Okay, let's continue the discussion about section 3.5, graphing techniques, transformations. Okay. So first, for example, we already have the function, square function, x squared. We can get its graph. The graph is this. A problem. But what happens if we want to get the graph of y equal to x squared plus 3? So how do we get the graph of the second function? Second function is slightly complex than the first one. So if you examine the evaluation, you will see that whenever you have x, you get the corresponding y value, you get x squared. And for the second function, you just simply add 3 to the value. So you add 3, possibly it's here. So every point you're going to move it vertically 3 units up. So the graph of y equal to x squared plus 3 is like 1, 2, 3. So it's like this. Okay, so you add 3, you more or less like push the graph of y equal to x squared vertically up 3 units. So when you add 3, you will shift the graph vertically 3 units. Okay, that's the understanding. Of course, you shift it up. And if you subtract x squared minus 4, here you have x squared minus 4, you just vertically move it down. This is a plus 3. This is a minus 4. So one, 2, 3, 4, negative 4. Just push or shift the graph of y equal to x squared vertically down 4 units. So minus 4, shift the graph vertically 4 units down. Addition, upward. Subtraction, downward. Okay, so this is a pretty straightforward observation. So whenever you just simply add or subtract some numbers from the function. So to summarize it, if you have a function y equal to fx and you already know the graph, assume you know the graph of this function, and you have two possibilities. One, if you have fx plus h is always positive, so h is a positive number, plus h, so shift the original graph vertically down, up h units. If you have y equal to fx minus h, so you shift the graph vertically down h units. So that's the summary. Okay. So add, up, down, minus, down, subtraction, down. Okay, so you can do this vertical shift. You can also you can also do the horizontal shift. Vertical shift is about y, then horizontal shift is about x. Let's see this. Example 3. Okay. We still use y equal to x squared. Now, in order to get the horizontal shift, we are going to change x. You see, originally, it's at this point. The graph is like this. I want to sketch the graph of x minus 2 squared. So how do I know where should I shift? Should I shift to the right or should I shift to the left? Let's check. X squared is x equal to 0 is origin. If I want to get 0 from x minus 2, I want 0 from x minus 2. I get x is equal to 2. So it means the behavior of the new function at 2 is identical to the behavior of the original function at 0. So 0 is shifted to 2 point. Okay, so you shift to the right because 0 becomes 2 or 2 becomes 0. There's a correspondence between these 2 points. Okay, so you minus 2, you shift it to the right. Okay, so this is the way to determine it if you are slightly confused. Of course, if you want to add a number, x plus 3, what happened? We do the similar thing. X plus 3 is equal to 0, so you get the corresponding point. So x is equal to negative 3. Negative 3. So negative 3 corresponds to 0. So it's like this. Minus 2 shift to the right. Plus 3 shift to the left. Okay, so this is the pattern. So to make it abstract, we have the following thing. So originally you have fx. Now we are trying to manipulate x. So we have 2 cases. If you have x minus h is positive. We always consider h positive. X directly minus x, not fx minus x. Minus h, fx minus x minus h, not directly, not fx minus h. Okay, so be careful. X minus h. When you have x minus h, let's check. You're going to shift the graph horizontally to the right. H units. Minus h to the right. And if you have f of x plus h, you add, then you shift the graph horizontally to the left. H units. So the addition corresponds to the left. This is to the right, so to the left. So we can shift it to the up, down, and left to right. Okay, so that's the transformation. Shift is a transformation. Okay, so if we combine this horizontal and vertical shifts, we can make the graph more complex. So the example. So we have this fx equal to x plus 3 squared minus 5. So our basic function is x squared. I want x squared plus 3. X squared has a graph like this. if you want fx equal to x plus 3 squared, you directly add 3 to x. You shift to the left. Check here. You shift to the left. So left 3 units. So -1, -2, -3. So it's like this. And then you get fx equal to x squared, x plus 3 squared minus 5. Minus 5 subtraction, move vertically down 5 units. So this is 1, 2, 3, 1, 2, 3, 4, 5. So this is the graph of the function. Here we do the horizontal first and vertical second. And you can also do the vertical first, the horizontal second. It does not matter. So eventually you will have the same graph. But middle step may are different, but the final answer should be the same. So you don't worry which direction you move first. You can move horizontal first, vertical second, or vertical first, horizontal second. You will get the same answer. Okay? The same answer. So the graph is this way. The graph is downward. Okay, so we already we can move the function, the graph of the function. Now we are going to stretch it, okay? So if we, for example, we have ups value function. Ups value function has graph like this. You have two diagonals, the diagonal of first quadrant and diagonal of the second quadrant. This is a graph y equal to x. And now we have 2 times ups value of x. 2 times ups value of x, let's just label the important point. When you have 1, the value is equal to 2. Ups value of 1 is 1, but times 2 is 2. When you have 2, the value becomes 4. Of course, when you have 0, it's 0, still 0. So that's the right part. And left part is similar. So when I have -1, ups value of -1 is 1, but times 2 is 2. When I have -2, ups value of -2 is 2, but times 2 is 4. So you kind of stretch the whole graph along the y direction. So it's a vertical stretch. If you multiply the function by a coefficient, it's greater than 1. It's a vertical stretch. Okay. Vertically enlarge the graph along the vertical direction. 0 is always fixed at 0 because 0 times whatever value is 0. Okay, this is a vertical stretch. And if we do not study the graph of y equal to 2 times ups value of x, we study y equal to 1/2 of ups value of x. Then what's that? So you check, you get the similar process, but the different graph. So when you have 1, ups value of 1 is 1, but times 1/2, it becomes 1/2. We'll get the 2, ups value of 2 is 2, but times 1/2 is 1. So it's still a straight line, but it's more flat. And similar thing happens for the negative part. 1/2 and 1. So you compress the graph along the y direction or vertically. So this is a vertical compression. It's a vertical compression. So what is a stretch? What is a compression? If the value is greater than 1, it's a stretch. If the value is less than 1 and greater than 0, it's a compression. Okay, so this value, it depends on the value of this coefficient. Big, stretch. Small, compression. Okay, so if we want to make the problem and the example more abstract, it's like this. If you have y equal to fx, and then you have a coefficient a is also always positive, then you have two possibilities. Y is equal to a fx, but this a is greater than 1. Very big, then this is a vertical stretch. Second, if you have y equal to a fx, but this time this a is between 0 and 1, small, like 1/2, 1/3, 0.1, this is a vertical compression. Stretch, you just enlarge it. Compression, just squeeze it. Okay, so the similar thing will happen. The similar thing will happen. So if you have y equal to fx and a greater than 0, let's check. If you have, instead of you multiply fx by a, you multiply x by a, and a is greater than 1. A is greater than 1. Okay? Then when this happens, for example, when a is equal to 2, when a is equal to 2, then you have 2x. 2x. If you let 2x equal to 1, you get x is 1/2. It means 1/2 corresponds to 1. The 1/2 corresponds to 1. Originally, fx needs 1, but with the coefficient 2, fx only needs 1/2, so you compress it along the x direction. So when a is greater than 1, you have a horizontal compression. Horizontal compression. So let's make this clear here. For example, this one. The same ups value function. Y equals ups value of x. And now this time, we're going to put 2x. 2x, let's check. What is the graph? When x is 1, 2x is 2, ups value of 2 is here. When x is 1/2, 2 times 1/2 is 1 is here. And similar process give you this. This function looks a little bit similar to the previous one. If you consider vertically, you kind of stretch it, but if you consider horizontally, you actually squeeze it or compress it. You see? So here it's this way, but horizontally you squeeze it, you compress it. So it's a horizontal compression. It's a vertical stretch. Okay? So vertical stretch, horizontal compression, they are related. When this a is greater than 1, it's a horizontal compression. When a is small, when a is between 0 and 1, it's a horizontal stretch. Okay? Horizontal stretch if a is between 0 and 1. Horizontal compression if a is greater than 1. So whenever you are not so clear about these concepts, just use ops value of x to demonstrate. Okay? So you will have, you consider it's a horizontal in the horizontal sense or in the vertical sense. Here, in the vertical sense, it's a stretch, but in the horizontal sense, it's a, you see here, you compress it, So it's a horizontal compression. Okay, so let's check. Assume we have a sine function. Sine function is a wave function like this. Or even we don't care what name you have. Let's just call it fx. It's like a wave function, onda. A wave function, just let's pick up more. This is 2 pi, this is pi, this is 3 pi, this is 4 pi, and 0. And this is 1, this is negative 1. Okay, so if we talk about fx is y is equal to 2fx. Y is equal to 2fx. This is greater than 1. You have vertical stretch. So how do we get a vertical stretch? When you have 1, it becomes 2. The x part does not change. So yeah, you still have pi, 2 pi, 3 pi, and 4 pi. And this time, originally it's 1, now it's 2. So you're going to have here you have 2, negative 1 becomes negative 2. Pi, 2 pi, 3 pi, and 4 pi. Okay, so this is the vertical stretch. Vertical stretch. And second, if we want the graph of y equal to f of 3x, f of 3x. So what do we have? So first, the y coordinate does not change, so the label is still between 1 and negative 1. It's still between 1 and negative 1. And you compress it, because here the 3 is greater than 1. You compress it along the x direction. So pi becomes a pi over 3, 2 pi becomes a 2 pi over 3, and 4 pi becomes a 4 pi over 3. So you have pi, 4 pi over 3. This is pi. 4 pi over 3 is here. This is 4 pi over 3. When x is 4 pi over 3, it's like this. When x is a pi, it's like 3 pi. When x is 2 pi over 3, this is pi, 2 pi over 3, and pi over 3. So you just divide everything by 3, because you multiply it by 3, you will go back to those points. And then you're going to have this, and this. You kind of just compress the function, the graph of function, to this new domain, 0, 4 pi over 3. Okay, so you just really compress it to the smaller domain. Because for any number bigger than 4 pi over 3, times 3 is greater than 4 pi. 4 pi is undefined based on our condition. Okay, so how do we sketch the graph? We just try to label some special point and get the corresponding points on the new coordinate system, and then we reproduce the similar curve, and that's the new graph. Okay. And in fact, you even don't care if this is a compression or the stretch. You just first locate the special point and then reproduce the curve. If it's longer, then this is a stretch. If it's smaller, it's a compression. And when you just handle x, you don't change y. When you handle y, you don't change x. So don't do them at the same moment. Okay, so here we always mention a positive coefficient, a. If you have a negative coefficient, for example, from y equal to x squared. If we want to study the graph y equal to negative x squared, you check it. When x is 0, it's x squared. Negative 0 squared is still 0. When x is 1, negative 1 squared becomes negative 1. Here is a positive 1. Here is negative 1. When you have 2, it's negative 2 squared is negative 4. So if you sketch it, it's like this. So negative of the function is so-called the reflection about the x-axis or vertical reflection. The reflection about the x-axis. So you get down, you flip it down. So the reflection about x-axis if you directly just have negative fx. Okay, so for example, if you have y equal to square root of x, the graph, then how do we get the graph of negative square root of x? We just flip. So this is a graph of y equal to negative square root of x. A negative sign, you reflect it about the x-axis. Similarly, you can reflect it about x-axis. You can also reflect it about the y-axis. So for example, the same thing, square root of function. And the graph is this. What happens if we talk about square root of negative x, not a negative square root of x? This is a negative square root of x. Here's a square root of negative x. If this happens, let's check. So first of all, when x is 0, you have 0. When x is 1, it's negative 1. Square root of negative 1 is undefined, so you cannot have the right part. You have to choose x equal to negative 1. X is negative 1. Negative x is positive 1. So square root of positive 1 is 1. X is a negative 4. Negative x is a positive 4. Square root of a positive 4 is 2. So it's like this. So when you put a negative sign in front of x directly, you kind of flip or reflect this graph about the y-axis. So from fx to f negative x, you get a reflection about the y-axis. Reflection about the y-axis. So you directly put a negative sign outside, you get a reflection about x-axis. You flip it down. And if you put a negative sign in front of x, you flip it horizontally about the y-axis. Okay, so this is the statement with the negative sign. So all the previous discussions about the positive stuff. So positive H, positive A, everything are positive. Now you have negative. Negative is a reflection. Positive is a stretch or compression and a shift. Okay, so there is a complete summary about this transformation. All these things are called transformation. Shift, stretch, compression, and the reflection. So you have a shift, you have a stretch, you have compression, you have the reflection. Reflection with a negative sign. Compression with a smaller greater than 1. Stretch is also with the coefficient a. Shift is with a plus h, either to x or to fx. Okay, so they are the 4 techniques, and these techniques are classified on page 251. What is the name of it? It's called the summary of graphing technique. So you have to be prepared for this table. This table is very, very important. Okay, so the next example, we are going to combine those techniques and get some complex, the graph of certain complex functions. Okay, so first we have our standard function, y equal to ops value of x. Step 1, shift left 2 units. Shift to the left. Left to right is about x. So you get y is equal to x plus 2. Shift to the right, left plus. Okay, shift to the left plus. And second, after you shift left 2 unit, shift up 3 unit. Okay, so you have this function. Shift up plus 3. Plus 3 at the end. Left to right, just directly plus or minus number to x. Shift to the up and down, add at the tail. Okay, and 3. Reflect about the y-axis. Reflect about the y-axis, you directly change the x to be negative x. Just change x to be negative x. You reflect it about the y-axis. Okay? If you reflect about the x-axis, you change y to be negative y. Okay? About y, you change x. About x, you change y. So this is the final stuff. The function of the graph of the curve is like this. So first, let's see how do we do that. You have this. You shift to the left. Shift to the left, and shift upward. Reflect about the y-axis. Reflect about the y-axis. This is a graph of it. Reflect about y-axis. Okay, that's a equation of the graph of the equation. Okay, so this section is very short and compact. It contains 4 different stuffs: shift, stretch, compression, reflection. And they are all related to the addition, subtraction, and multiplication by a number, either positive, negative, greater than 1 or less than 1. So you have to really do the exercise and get the correspondence about the addition, subtraction, greater than 1 or less than 1 part. So there's no easy way to memorize all of them. You just do the practice and you will get the feeling. Okay? So that's the section 3.5 graphing part. And now let's do the section 3.6 mathematical models building functions. So we study a lot of functions. Now let's try to use a function to study some problems from geometry, physics, and the real life. Okay? Section 3.6 mathematical models building function. Okay, so first example. We have a graph of function. Y is equal to x squared minus 1. So we know that you have y equal to x squared minus 1. You shift it downward 1 unit. So it's like this. And you have a point on this graph. And then you can connect the point with the origin. The first question, express the distance. Express the distance d from P to the origin O as a function of x. Okay, express the distance d from P to the origin O as a function of x. So first of all, distance, this is d. Distance, we have distance formula. Assume this point P has xy coordinate like x and y. Then distance formula is x minus x coordinate square plus y minus y coordinate square. The origin has a coordinate 0, 0. So it's x minus x square, y minus y square. So it's a square root of x squared plus y squared. This is a corollary of the Pythagorean theorem. And this point P is on the graph. On the graph, yx satisfies the equation. So P is on the graph. So y is x squared minus 1. So the distance is x squared plus x squared minus 1 squared. X squared plus, this is x squared squared minus 2x squared plus 1. So it becomes x to 4 minus x squared and plus 1. So this is the answer. Express the distance as a function of x. So this is the distance as a function of x. Okay, and then let's check what, the second question. What is d when x is 0? X is 0, this point. This is x equal to 0. They want to know the distance here. Let's check. D square root of x is 0 minus 0 and plus 1 is 1. Sure, because here is negative 1. From 0 to negative 1 is 1, so distance is 1. What is d when x is 1? When x is 1 is here, this point. This point, the x coordinate is 1. This is 0, 0, 1 is still 1. But let's check from the formula. You get a 1 to 4 minus 1 squared and plus 1. 1 to 4 is 1, minus 1 squared is 1. Square root of 1 is still 1. So distance is still 1. So no surprise. And now we can say what is the distance when x is root 2 over 2. Well, it take some computation, so the distance, let's do here. Square root of root 2 over 2 to 4 minus root 2 over 2 and plus square and plus 1. Root 2 over 2 to 4 is root 2 to 4 and 2 to 4. Root 2 to 4 is 4. 2 to 4 is 16, so it's 1 over 4. So it's a square root of 1 over 4. Here is 1 half and plus 1. So if you compute it, it's 3 over 4 and then square root. Anyway, just do the computation. It's not that difficult. Okay, so whenever you have a x value, you can compute the corresponding distance. And then, so far we don't have more technique to solve the stuff, but we can use some graphing utility to graph the function. CTE. We can use, of course you cannot use it during the exam. To graph this d of x, the distance function. So let me see. If you graph it, it's possibly like this. So this function has this way, not that way. This function has a minimum value at a certain point. So from the calculator, one can see that this value is possibly 0.71. we don't care how do we get it, but it's just from the graphing utility, we can see when x is possibly 0.71, d is minimum, is approximately 0.87. So what does this mean? This means when x is 0.71, possibly here, this distance is the short, smallest distance, the closest point to the origin. So that's the idea. So we can use the graph to get this. Okay? Okay, so that's the idea. So we have the parabola and we get a point. We have a parabola, we get a point, we measure the distance. Distance is a function of x, and if we know more about the property of x, we can find the point, the closest point to the origin. Yeah, that's the idea. The second example. Assume we have a parabola, again, the parabola. This is a 25. Y is a 25 minus x squared. And for whatever point in the first quadrant, x and y, it gave us a rectangle. It gave us a rectangle. This is 5. This point is 5. We want to express the area A of the rectangle as a function of x. Okay, so area of the rectangle as a function of x. Area of rectangle, areas, base times height. This is base. This is height. X times y. This is y, this is x. And the point is on the graph, so y is a 25 minus x squared. So 25 minus x squared. It's a 25x minus x cubed. And you see here, in order to form a rectangle, we only allow the point is on this part. In order to form a rectangle, if you have a point here, you have this kind of rectangle. You have a point here, you have this kind of rectangle. So the x should be between 0 and 5. This is x. It should be between 0 and 5 to have a rectangle. Okay? And if we use some graphing utility to graph this A in terms of x, it looks like this. So when x is 0, at this point you cannot construct a rectangle. You only have a vertical segment. The area is 0. If you let x equal to 5, you get a horizontal segment. The area, of course, is also 0. So it's more or less like this, 0 and 0. It reaches certain maximum value at a certain point. And from that graphing utility, we can see that when x is approximately 2.89, the corresponding area has a maximum value is 48.11. And how do we get those approximations? Based on the graphing utility. So you cannot use this in the exam, but you just know that we can use functions to determine where we get the maximum area of the rectangle. So it's around 3. And in the calculus, you will see how and why we can reach the maximum area at that point. Why it is that point, not other point. Okay, so this is the example in in section 3.6. And there's another example. It highly depends on the geometry, so we are not going to discuss it. You should read this third example, making a playpen. If you have question, we can discuss it. That one is more complex, and it does not contribute some new idea, but it's highly related to the geometry. So up to section 3.6, we have our second exam. So you should do the exercise and the practice exam. I'm going to give you the answer key quickly, and you compare your answer with the answer key. Don't directly read the answer key. You must do it, the practice exam, by yourself. Okay? Okay. So do the exercise, do the practice exam. Thank you. We stop today.